All right, welcome back to part 2 of chapter 8, t-tests. We're going to be in this video we're going to be kind of walking through the 4-step sequence that the book outlines for forming a hypothesis, selecting a critical value, finding the test statistic, and then making a decision. Along the way, we're also going to find effect sizes and calculate the confidence interval. So let's get into it. The first step that we're going to be doing here is that we're going to be selecting a hypothesis. Now this is going to be very, very similar to what we did last chapter, where we identify a null hypothesis and an alternative hypothesis. And the definition of what those hypotheses are is going to stay the same. So, and that's going to be true for all chapters moving forward, that the null hypothesis is always going to be the hypothesis that asserts that there is no real difference here. And so the null hypothesis is that the sample is not different from the population. Now, the wording here is very carefully arranged. It doesn't say that the sample is the same as the population. It just means that it is not different. And while those might sound like similar things, basically what we're doing is we're trying to look for any evidence of differences. So that's why it's worded this way. So if we are going to find differences, we can find that in the alternative hypothesis. So the alternative hypothesis is that the sample is different from the population in some way. So if it's a two-tailed hypothesis, a two-tailed test, then we would say that the sample is different from the population. If it's a one-tailed test, then we would say that the sample is greater than or less than the population. And much like last time, whichever one you choose for your alternative hypothesis, the opposite of that is going to be the null hypothesis. So if I said that this is going to be greater than the population, then the null hypothesis is that it is going to be less than or equal to. So, in the case of our example, how that would look, we were testing whether or not there was any difference from 11, right? So I would honestly probably formulate the alternative hypothesis first, where I would say the alternative hypothesis is that our sample, those 5 individuals, do not stay for 11 sessions. That is different. Maybe it's greater, maybe it's less than, but that is different in some way. So it's not the same as 11. And the way that we would express that is the HA symbol, and then we would say X bar, so our sample is not the same as the population. So mu, X bar is not equal to mu. The null hypothesis, then, remember, if that's the alternative hypothesis, the null hypothesis is going to be equal to, because that's the opposite of not equal to. So that's going to be that that X bar, our sample mean, is the same, is equal to our population mean. So that is how we would frame this for our previous example. So y'all know that I love drawing these things out. So one of the things that I didn't do but that I wanted to do is to draw out our distribution here and to think about where these critical values are. That's what we're doing in this section right here. So the way that we would find it is we have to first establish what the alpha value is. Now, as I mentioned last chapter, it's almost always going to be 0.05 just because that's what the scientific community uses. However, sometimes it's smaller, sometimes it's greater. So just keep your eyes peeled. If you don't see anything about the alpha value, just assume that it's 0.05, but I usually try to tell you which it is. So if we are going to do that, so we know that it's a two-tailed test, right? So we're looking at this and it's not less than or greater than, so we know it's a two-tailed test. So how do I find these values? How do I find what portion of the distribution should be shaded as the rejection region? The way I do that is I pop over, oh no, sorry, that's where I record. You saw behind the scenes. So that's where we come to our critical value calculator for t-tests. So for us, we have a p-value of 0.05, that's our alpha level. Our degrees of freedom, remember our degrees of freedom is going to be 5 minus 1, which is going to be 4. And then we're going to hit calculate, and that's going to give me these two values, one for a one-tailed test, one for a two-tailed test. So for a two-tailed test, we're going to go with this right here. So plus or minus 2.78. And so whenever I look back over this, that's exactly what I'm seeing here, negative 2.78 and positive 2.78. So if our t-obtained score falls anywhere in these rejection regions, then we can reject the null hypothesis because we have enough information to confidently say that our sample is not the same as 11. If we wanted to be really, really conservative here, we can knock this over to 0.01. So what would that look like? So if I wanted to be extra conservative and extra careful here, I can turn this to 0.01 instead of 0.05, which means that I'm going to be looking for the 1% likelihood in those tails. So very extreme values there. So I'm going to hit calculate, and wow, it moves up to 4.6. So it almost doubles from where it was. So a huge increase if you were to change this to 0.01. That would make the t-critical much more extreme. So again, we're going to find the test statistic. So we popped in our sample mean, our population mean, and now our sampling error. And the sampling error is going to be our standard deviation divided by the square root of n, right? And that's how we get these numbers. That's how we get 1.33. And that's going to give us a t-value of 0.05, which if we think about where that is in our distribution is probably somewhere right around here, which just is not enough to reach that positive 2.78 critical threshold. So what does that mean? Basically it means that we do not have a t value that is in our rejection region in either extreme over here, which means that we are going to fail to reject our null hypothesis. So again, it's not, and I know that the wording is very annoying here, but we can't reject the alternative hypothesis, nor can we accept the null hypothesis. Instead, we can either reject the null or fail to reject the null. And what we're saying here is that we are failing to reject the null. We don't have enough evidence to say that they are different. We're still saying there could be a case that they are in fact different, but we just don't have enough evidence here. So that means that we would say that our patients do attend therapy on average for 11 sessions. Even though the actual number is 12.4, what we establish is that once you account for the variability that all patients have, that is no different from 11 sessions. The way that we would write that is something kind of like this. And so this might be a good idea to hold on to this kind of language so that whenever you're in Research Methods 2, you can look back over your notes and you can know exactly how to write your results section. So I would say that I fail to reject the null hypothesis. Based on a sample of 5 patients, I can't conclude that the average patient, and then I put the mean values there, stay longer or fewer than 11 sessions. And then that's where I put the statistical notation information. So I'm going to be putting the t, which just lets the reader know that this is a t-test that I did. I put the degrees of freedom in the parentheses. We're going to do that from now on. Anytime we have a t-test, we're going to put that in the degrees of freedom next to it. That's going to be equal to the t obtained value, and then we're going to say p is greater than 0.05 because we were not able to reject the null hypothesis. So was that surprising? I don't think it was, because we had a very small sample size. And one of the things that I was trying to emphasize is that whenever you are working with t-tests, it pays to have more people in your distribution. And you can kind of see that here. So this drawing looks at the distributions and how they spread over with different sample sizes. So how do we interpret this? I would say think about where these tails are. So you see these tails. Which one is highest up? Which is the thickest tail? The thickest tail is this one right here, the light green one, because it's only 2 individuals, a very small sample size. But basically what that means is that with this distribution, it's not all that uncommon to find extreme values. Once we start having more than 30, we're going to start getting really close to a z distribution. So any more than 30, you can kind of see that the tails down here are very close together and they're very close to the bottom, which means that this area down here is very unlikely to occur, which is part of the reason why, if we're trying to reject the null, having a large sample size makes it easier to do so because of the way this distribution is formed. That the more people you have, the more normal it becomes, and the more normal it comes, the more extreme the tails are, which is a good thing for us. So as the sample size increases, the tails get narrower and the t-critical values get smaller. And why do they get smaller? Because the t-critical values are going to get closer and closer and closer to our z distributions values. I emphasized that on the previous video in case that wasn't super clear. All right, so here are some examples of t-criticals just to kind of highlight what I was talking about there. Let's just focus on well, this is kind of hard to interpret, but the way you interpret this is that this is if you're looking for an alpha level with a 1-tailed test, and this is if you're looking for an alpha level for a 2-tailed test. And I just want to call your attention to these numbers, so 5 and 10, 2.5 and 5, 1 and 2, 1/2 and 1. The one on top is half of whatever this one down here is. That's not a coincidence. The reason why is because this is a 1-tailed test, this is a 2-tailed test. You may remember whenever we were identifying what proportion or what probability belongs in each tail, it depends on if it is a 1-tailed test or a 2-tailed test. If it's a 2-tailed test, you're taking all of your alpha level and you're going to be splitting that amongst the 2 tails. If you're not doing a 2-tailed test, you're taking that alpha value and you're putting all of it in one part of the tail. In one tail, not in both. So you don't have to split it up. So the degrees of freedom, as they increase, this is another way to think of like the sample size is increasing as we go down. And as we go down, you can see that basically our t-critical is going to get smaller and smaller and smaller. So as we move down this way, the sample size increases and this gets smaller. If we wanted this really strict 0.005 instead of just 0.05, you can kind of see what it would take to reject, some of these. These are really high t-scores to reject those. But as they increase, you can see how it, begins to kind of stabilize at that point. All right, so confidence intervals. Let's talk a little bit about confidence intervals here. So confidence intervals are another way to assess the validity of a hypothesis. So they're used much more frequently than they were 10 years ago. If you look at a journal article published 10 years ago, you may not find a whole lot of confidence intervals there. If you find one that was published a year or two ago, you're going to find a lot of confidence intervals. So what are they? What are confidence intervals? Confidence intervals are a way to look at how likely new data are going to fall in your proposed distribution. That's a really, really fancy way of saying that you can use the confidence intervals to say, with 95% degree certainty, any new value we find is going to fall within these 2 parameters. And we can use that to actually do hypothesis testing if we want to. So here are the ingredients that we're going to be using. They're the same ingredients that we've been using so far. They're just going to be used in a new way here. So the ingredients that we need are going to be the t-critical score, the S, so the standard error of the sample or the sampling error, and then the sample size. Those are the ones that we need. All right, so here is the formula for that. We are going to plug in our t-critical, and then we are going to plug in our sampling error. So why is it that we're putting in the t-critical instead of the t-obtained? That's a great question. Thank you for asking. We're putting in the t-critical here because if you look back over these charts, that's exactly what we're doing. If we want to know, for example, if somebody is within 5%, right, so 5% confidence, then we're going to be using these t-criticals because these are going to tell us what, whoops, sorry. Ooh, I hit the hit the keyboard with this big stylus that I use to draw things on. But if you, basically what we're saying is that with this t-critical, we're showing here are the rejection regions. And then those rejection regions we're going to change. We're basically going to scale them using our standard error of the sample. So if you have, whoa, that's a really bad, that was supposed to be a straight line. If you have a distribution like this, then you can use your confidence intervals to tell you exactly what the scores are where these t-critical thresholds are. So basically it's like taking these t-criticals and turning them into an interpretable format where you can understand what those are. Because otherwise, a t-critical, like, what do these even mean? These are all created for a standard normal distribution, so they're not really all that interpretable. If we want to interpret them, then we have to standardize them using, not standardize, we need to unstandardize them using this formula. So let me give you an example here. So the margin of error is going to be created using those, and the confidence interval is going to be adding and subtracting that margin of error from your sampling mean. So basically, a 95% confidence interval is saying that the interval in which you've created, 95% of all samples that you could possibly choose from this population are going to fall in between these two numbers. A low fence, they call them fences, a low fence and a high fence. If a sample falls outside of that interval, then what we are going to say is either that sample is very, very rare and unlikely, or it is different from the population. So that's very similar to our notion of t-tests, right? That with t-tests, what we're saying, if we have p less than 0.05, is that either these outcomes are exceedingly rare, because they're just by chance, but very unlikely, or that they are fundamentally from a different distribution. They're fundamentally from a different population. All right, so we are going to calculate our margin of error, and then we are going to basically, and this is where the margin of error goes, basically add and subtract that margin of error from our sampling mean. So here are our ingredients, right? So these that we mentioned. So we are going to use our previous example to do this here. So here is our formula now. So with our formula, to get a 95% confidence interval, the first thing that I want to do is I want to find the margin of error. So to find the margin of error, I'm going to be plugging in these values. What is the t-critical for this alpha level? Generally speaking, I'm going to say this generally speaking, but you're only really supposed to do confidence intervals whenever you have a two-tailed test. There may be some instances where I ask you to calculate a confidence interval with a one-tailed test. That's just going to make our interpretation of that confidence interval really difficult and messy. But I find that, if I'm giving you something on the exam and I tell you to do all these steps, but I don't tell you to do a confidence interval, that might be a dead giveaway that it's a one-tailed test, right? So that's why I usually ask you to do two-tailed for both. So why am I bringing up two-tailed here? Because that changes the nature of the t-critical formula. So for us, the t-critical formula was 2.78. Right? So we're going to put in 2.78 there, and then we're going to multiply that by the sampling error, which is, if you remember, 1.33. So this is going to then give us, our margin of error is plus or minus 3.69, which basically means that any new sample that is more than 3.69 above or below our sampling mean, right there, the 12.4, is going to present a problem for us, because that must mean that perhaps, this was really unlikely, or in fact, we can reliably say that our patients stay a different time period than 11 sessions, not equal to that. All right, so if we plug in these numbers, if I am adding 3.69 to 12.4, I'm getting 16.09. If I'm subtracting from it, I get 8.71, which basically means if I want to reject the null hypothesis, our sample mean needs to be somewhere greater than 16.09 or less than 8.71, which is quite a bit. So why is it that these numbers are so large? Because we had enough variability in our sample to say that there's quite a bit of variability in the natural course of this behavior, so we're not super confident in it, and that's why we have these kind of really, really large margin of errors. So basically those values that we calculated represent these thresholds right here. So we can think of them, if we want to, as a negative 2.78 t-critical and a positive 2.78 t-critical, or we can think about them as 8.7 or 16.09, because that 95% confidence interval basically transforms that into an interpretable, meaningful value instead of just t-criticals. So let's say in our previous example, instead of doing a 95% confidence interval, we want a 99% confidence interval, because our alpha value is now 0.01. So we know these are exceedingly unlikely values now, because we're looking at the bottom and top 1%. So pretty much everything else is going to be the same here. The big difference is that we are using a new t-critical value. That t-critical value is 4.6 now. But when we take that sampling error, 1.33, we multiply it by 4.6, that gives us 6.12, and we're going to add and subtract 6.12 to 12.4, which is going to give me 6.28 and 18.52. So that means if we look back over at our distribution right here, that this is going to be even further over here, and this is going to be even further over here because we are using different alpha values. But otherwise, it's exactly the same. So we can now say that we are 99% confident that if we were to get a new sample, that it's going to fall somewhere between 6.28 and 18.52. All right, so we can use confidence intervals to make decisions about our hypothesis. If the confidence interval is not if the population mean does not fall inside the confidence interval, then we can reject the null hypothesis. So if 11 did not fit between these two values, then we can reject the null hypothesis. So this is yet another way to check your work. If you go through the standard routes and you reject the mean, or you reject the null, and then you do the confidence intervals and you don't reject the null, that must mean that somewhere there's an error that you're making, because those two should be the same. They should agree with one another. All right, and then finally the effect size. This is the last thing I wanted to talk about. The effect size is going to be exactly the same as it was for last chapter. This is Cohen's d, if you remember Cohen's d. So Cohen's d is going to be equal to x bar minus mu divided by the standard deviation. So and remember, the standard deviation is the sample standard deviation. So I guess technically it's not a sigma, it is an S. But other than that, it's going to be the same, and even the guidelines for what creates a small or a large effect size is the same too. So we can plug those in. So here we find a small moderate effect if we were to plug these things in. So that's going to give us 12.4 subtracted by 11 over 2.97, because that was our standard deviation, which goes 1.4 over 2.97. And if you have a calculator, you can figure that out. I don't know what it is off the top of my head. Sorry. I got 0.47. So that is, do I round? Nope. Yeah, so that is between small and moderate. So what we're saying is that this is a pretty moderate effect size that we would have had here. But again, this is one of the things that we're not exactly supposed to do because we didn't reject the null hypothesis. So we usually only do that when we reject the null hypothesis. But I may ask you to do it on an exam just to show that you can do it. And that is it. So the next video I'm going to upload is going to be a quick kind of example going from start to finish with that. And if you have any questions, I will see you later. So don't hesitate to reach out, Feel free to email me. We can set up a time to meet or to talk. And thank you so much. I will talk to you later.